You want to create your own aircraft simulation? You've come to the right place. We're on a journey to build a sim from the ground up. Today, we're dropping bowling balls from the stratosphere. To recap the series, we first introduced the primary components of a full aircraft simulation. We then explained and coded the 6-DOF equations. In the third lesson, we explained the Euler kinematics and performed our first simulations with a sphere falling in a vacuum under gravity. In this lesson, we take a few steps forward. We explain the navigation equations, we build in an atmospheric model, and we add an aerodynamic model. Our objectives are first to cover the navigation equations. These equations capture the position of the vehicle as it flies through space, acted upon by gravity or aerodynamic forces. Speaking of aerodynamic force, we're going to need relative velocity, angle of attack, and angle of sideslip, because these variables determine aerodynamic force from an aerodynamic model for our vehicle. We'll have that for our sphere. We'll also have an atmospheric model. This will capture changes in air density and other air properties as the sphere will fall from high to low altitude. We'll code these additions in Python, and then we're going to run some verification checks, drop in different types of spheres, making sure that things make sense. We got a lot to get through, so let's go. Here's the position equation in vector form. The notation follows Stevens and Lewis and is also discussed in section 1.2. Rightmost is the vehicle velocity in the body coordinate system of the vehicle center of mass with respect to the point T. This is pre-multiplied by a direction cosine matrix that transforms velocity in the body coordinate system to the northeast down coordinate system. The DCM, note, is a function of vehicle attitude, the Euler angles phi, theta, psi. On the left-hand side is the vehicle velocity, notated as the position vector derivative, p dot, resolved in NED with the derivative in the inertial frame. Let's break this equation out into its elements. We have velocity in the body axes and the DCM from body to NED on the right. On the left, the position derivatives in NED. So we integrate those position derivatives to get the state of the equations, the position, P1, P2, P3, denoting distance from the origin at T to the vehicle center of mass as quantified in NED. And with these equations, we essentially get position by integrating velocity resolved in NED. Our first objective is complete. Relative velocity is important because its magnitude directly relates to aerodynamic forces. It's the inertial velocity minus the wind velocity resolved in the body axes. It captures motion with respect to the atmosphere. If the wind moves with the aircraft, then we have a tailwind, and wind velocity is subtracted. If the wind moves opposite of the aircraft, we have a headwind. It's negative valued. So by the formula, the wind component is added. Note, wind is commonly quantified in the northeast down coordinate system. So we must use the NED to body DCM, which we've covered in section 1.3, to get wind in the body coordinate system. The aerodynamic forces not only depend on relative velocity magnitude, but also on its direction, that is, the angle of attack and angle of sideslip. Here's an aircraft with a relative velocity vector. We will illustrate the angle of attack and sideslip through two rotations of the body axes. First, perform a left-hand rotation about the body y-axis so that the relative velocity is in the xy plane. This rotation creates a new coordinate system referred to as the stability axes. Again, xs, ys, and vrel are all in the same plane. The angle alpha that gets the velocity vector in the xy plane is the angle of attack. Angle of attack is positive when the relative wind is coming from below, as shown here. Mathematically, we perform this rotation with the planar rotation matrix about alpha. This is the DCM from body to stability axes. Now, rotate the stability axes about ZS so that XS is aligned with VB rel. In doing so, we no longer have the stability axes, but a new coordinate system referred to as the wind axes, denoted with W. The rotation through the angle beta is the angle of sideslip. Sideslip is positive when the relative wind is coming from the right, that is, in the pilot's right ear. As shown here, sideslip is negative. The transformation from stability to wind axes is with the z-axis planar rotation matrix about the angle beta. In summary, we have defined stability and wind axis coordinate systems through rotation of the body coordinate system about the angle of attack and the angle of sideslip. Their product is a direction cosine matrix that allows us to transform a body axis vector to wind axes. The computation of angle of attack, sideslip, instantaneous body to wind direction cosine matrices. These are all involved in correctly resolving aerodynamic forces in our flight simulation. As we're going to see, the wind axes are directly related to how lift, drag, crosswind, or side force are resolved. We wish to build a model of the aerodynamic forces acting on a sphere in our simulation. Our translational equations are resolved in the body axes, so we require aerodynamic forces, denoted Fx, Fy, and Fz, in the body axes. We assume the sphere is not spinning, so there's no lift due to the Magnus effect. This means that for some relative velocity to the atmosphere, there's a drag force that acts opposite the relative velocity direction. We can define the drag direction as the x-axis of a right-handed coordinate system with lift, drag, crosswind forces. We denote the lift-drag coordinate system, or axes, with the letter D. We need to relate forces in the lift-drag coordinate system to those in the body coordinate system. Let's first consider a special case where the relative velocity vector is out the positive body x-axis. Then angle of attack and angle of sideslip are 0, so that the wind axes are aligned with the body axes. Now, imagine you're on the sphere, facing the positive x-axis. The airflow pushes you against the sphere so that you experience drag opposite of your motion. Therefore, the drag is opposite of the wind axis x direction. And in this particular case, drag is opposite the body axis x direction. But of course, the body velocity vector can be in other directions, like in our previous configuration. Notice that the wind axes are aligned with the lift-drag axes, but act in opposite directions. And recall, we've developed the DCM for body to wind axes. So now we can relate lift, drag, and crosswind forces to body axis forces. And this is needed in our simulation where translational equations are resolved in the body axes. Let's examine the terms in this formula. We have the lift, drag, and crosswind or side force, which is natural for measuring forces in a wind tunnel and often how aerodynamic data is reported. The negative sign accomplishes the wind axis transformation to lift to drag axes. We have a direction cosine matrix relating body to wind axes where its transpose makes it wind to body. And so, we have a formula to transform aerodynamic lift, drag, side force data to the body axes, and this completes an objective. It's essential to integrating the aerodynamic model within our equations of motion. We need to quantify the drag force acting on the sphere. Here, we simply set the drag coefficient to 0.5. No other forces act on the sphere in this aerodynamic model. Our force vector then has only one non-zero component, the drag force. But when resolved in the body coordinate system, of course, all three elements of the force vector could be non-zero. The drag coefficient, note, is non-dimensionalized with a reference force that is the product of the dynamic pressure, Q bar, and the reference area. We get the dimensional drag with the product of drag coefficient, dynamic pressure, and reference area. Dynamic pressure is 1/2 times air density times airspeed squared. Airspeed is the 2 norm, or the square root of the sum of the squares of the relative velocity vector, and the reference area is simply the frontal area of the sphere. We now have the mathematical pieces to implement an aerodynamic model of our sphere in our sim. The sphere model was quite simple, just a drag force, and we assumed it was constant. Now, if we had time-varying lift, drag, side force for another vehicle, our approach is general so that we can accommodate that in our development so far. We have one more piece to implement our aerodynamic model, though. That's the atmosphere. From the drag force expression, we identified several variables necessary to dimensionalize the drag coefficient into a drag force. This equation captures changes in aerodynamic force due to changes in air density as a function of altitude. Also, if we're flying through a jet stream, there could be winds, headwind, tailwind, that could affect the airspeed term. For now, we don't consider such winds as part of our atmospheric model, but we will capture how air density and other atmospheric properties change with altitude. And for this, we use the US Standard Atmosphere 1976 model. It's an idealized steady-state representation of the Earth's atmosphere from the surface to 1,000 kilometers altitude. The document contains 4 parts, defining constants and equations, the atmospheric model, trace constituents, and atmospheric data tables. At first, we may be tempted to transcribe our atmospheric model from the data tables in the back of this vintage report, but there's a lot of data, and depending on how many points we want to include, it could be an onerous, time-consuming task. But since this is a well-known model, I thought maybe someone has already taken the time to import the data into a digital form. And sure enough, folks have already put in the work with the USSA 1976 Python package. So we import this package into our sim and call the atmospheric data into our simulation for interpolation between points in the tabulated data. Recall this flow diagram from the previous section representing the integration process of our state equations. I first tried using the USSA 1976 Python package directly in the simulation state equations, calling its tables at each time step from its built-in interpolators to the tabulated atmospheric data. When used in this way, the simulation slowed down significantly to where it would take longer to integrate than the total duration of the simulation. So I decided to load the atmospheric table from the package at the start of the simulation. This was stored as a bunch of column vectors, and then those data vectors were passed into the state equations as inputs and interpolated with a custom fastinterp function. The fastinterpolator used linear interpolation to a single point, and if outside the data table, the last value was held constant. So this approach avoided any significant increase to total integration time. With the math and the atmospheric data out of the way, we're ready to build these new additions into our Python simulation. Last time, we went through this simulation process involving integration of 9 state equations. Now here we're adding the aerodynamic model, the atmospheric model, and also navigation equations to the equations of motion. The addition of 3 navigation or position equations means we have a total of 12 states to integrate. These are the previously covered translational, rotational, and Euler kinematic equations. And the 3 additional navigation equations, and in addition, we have several auxiliary equations, including air data, angle of attack and angle of sideslip calculations, direction cosine matrices, from body to northeast down, from wind to body, and with their transpose, vice versa. An atmospheric model, and an aerodynamic model. To contain our new additions, the previous file structure has expanded. We're adding 4 new folders. We have a vehicle model folder containing a folder named sphere, which contains a sphere Python script that defines various sphere properties for simulation. We have a tools folder that for now contains the fast interpolation script. We also have a saved figures folder, which is obvious from its description. Let's briefly review the main program driver and the flat earth equations of motion scripts where we've made the primary updates to the sim. Here we are in the main program driver of the simulation. Notice now we're importing the atmospheric package. We have an interpolation and a sphere script. When we initialize the simulation, now we're getting the atmospheric tables from the atmosphere package, storing vectors of interest, that is altitude, air density, speed of sound, and gravity, putting that data into a dictionary we call AMOD. Now, previously that was aircraft model, but that conflicts with atmospheric model. So we're making AMOD atmospheric model. The aircraft is now vehicle, and so we call that VMOD. And in this case, we're selecting bowling ball data from our sphere script. And part of the sphere script is to calculate other things associated with the sphere selected. That includes terminal velocity, which we print out, and then the numerical simulation of the terminal velocity is compared in the terminal window here. And you can see some numerical results that we'll come back to a little later on in the lesson. Here's our initial condition. Nothing new here. Storing the initial condition. Setting our time conditions as before. Part 2, now we're numerically integrating the governing equations. And now we have the position equations, the atmospheric model, the aerodynamic model. Really all of that is operated and used inside of the numerical integration routine with the flat earth equations of motion script, and we'll get to that in just a moment. After the numerical integration, we have this state data, 12 states and time steps. We post-process the state data to get quantities like airspeed, angle of attack, angle of side slip, and Mach number. Now, our governing equations could be posed in stability form. There's the stability equations, which would have VT dot, alpha dot, beta dot, but we don't do that here. Instead, we have it in the body coordinate system resolved, and so we have to compute air data like Mach, alpha, beta as a post-processing step. Now, into the flat earth equations of motion, we're bringing in the interpolation script. There's our function. We have the vehicle model and the atmospheric model coming in. A change from last time, now computing the trig operations on the Euler angles and storing those as variables so that they can be used once and not repeated several times. Mass and moments of inertia, as before. Altitude is the opposite of the down direction. So we get the current altitude, and then we use that with our atmospheric data and interpolate to the current altitude. That is air density to the current altitude, h in meters, and speed of sound. Speed of sound here is just used for Mach number calculation. Also in the Mach number calculation, we need the airspeed. And so here it is, the square root of the sum of the squares of our body resolved velocity. Here's dynamic pressure. And here are some conditionals. Now, this is necessary to avoid divide by zero in angle of attack and angle of sideslip computation. We interpolate gravity. Here's an option to set gravity constant if we would like to. We have to manually select that in the script right now. Aerodynamic force. Here we go. Drag. So CD times Q bar times A ref. Drag force. No problem. Here's us now resolving that drag force in the body coordinate system according to that direction cosine matrix that goes from the aerodynamic coordinates that resolve drag, lift, side force to body. And so in that DCM is trig operations on alpha and beta, as you can see. No moments on this vehicle. That will be coming soon in other vehicles that we will model. And now our state equations. We've gone through these translational and rotational equations. And last time we went through these kinematic equations. And this time we have three new equations, our position equations. All right, let's run a few verification checks. Let's test terminal velocity prediction. And for this, we're going to drop a .50 caliber lead musket ball. We'll compare the numerical simulation to a value that's determined analytically from a formula. And for this, we're going to hold atmosphere density constant as well as gravity constant. For the initial condition, while we have a precaution in our code that allows us to set U to 0 initially to avoid division by 0 for angle of attack, an alternative is to set U to a small value. The pitch angle is minus 90 degrees. And this points the x-axis down for reasonable angle of attack and angle of sideslip computations. We set the initial altitude to 10,000 meters or about 33,000 feet. To derive an analytical formula for terminal velocity, note that in this example, the 6-DOF equations just reduce to the axial velocity equation. Now, at terminal velocity, the sphere is no longer accelerating, so U dot is 0, and we just have a balance between drag and gravity. So solving for the airspeed, we get an equation for terminal velocity. Let's run the simulation now to check our terminal velocity prediction. Here we are in main program. I've set the sphere to musket ball. This is just a function defined in the sphere's script. I've updated the initial condition. I've updated the final time condition. I happen to know that 100 seconds is enough for this ball to reach terminal velocity. Into the equations of motion, I've set air density to a constant 1.2 kilograms per meter cubed, and I've set gravity to a constant 9.81 meters per second squared. We observe motion only along the x-body axis as expected with pitch angle at minus pi over 2. The analytical terminal velocity prediction was 78.7 meters per second, and our simulation accurately predicts this to at least 2 decimal places. Here we use forward Euler integration with a time step size of 1/100th of a second. Now, let air density change with altitude according to the 1976 atmosphere model. Beyond 35 kilometers, air density is essentially zero, and then it monotonically increases with decreasing altitude, approaching 1.22 kilograms per meter cubed at sea level. Now, since the ball is dropped in thin air initially, how would you expect the airspeed profile to evolve? We'll use the same initial condition as before. Back in our code, we turn on the air density interpolation. We turn on the gravity interpolation. Save it. And we run the sim. We notice a different velocity profile than before. Let's break down what's happening. First, we observe increasing airspeed up to a much higher value than in the previous example. This is attributed to the ball accelerating for a longer period due to the thinner air. That is, gravitational force is initially larger than the opposing drag force. Airspeed continues to increase until about 25 seconds. It peaks out because drag begins to overcome gravity, so that the net force acting on the ball is about to change direction due to the present speed of the ball and the thickening atmosphere. After this point, the net force is indeed in the opposite direction, with drag decelerating the ball. This deceleration continues as air density approaches the sea level value. We can see the ball approaching the terminal velocity for gravity and density near sea level. As the velocity vector points out the body x-axis, there is zero angle of attack and zero side slip throughout. We can see the Mach number peaks at just over 0.35. Now, let's explore dropping a bowling ball from 30 kilometers or 98,400 feet in altitude. At this altitude, the air is very thin, and the bowling ball will continue to accelerate for a longer period of time than in the previous example. Once we obtain the results, let's think about the validity, that is, how true the results are to the actual physics of the system. Back into main program. We update our sphere. We update the initial altitude. We update the time duration, which I happen to know is sufficient for this example. And that's it. The atmospheric model's on from the previous example, so we just run the program. Because the ball accelerates for a longer period, we notice the peak velocity happens later at about 50 seconds, and it's quite pronounced, exceeding 300 meters per second early on before drag begins to overcome gravity and decelerate the bowling ball. The ball falls for over 3 minutes straight down, so that altitude versus north and east show the straight trajectory. It's dropped directly above northeast down coordinates, so that north and east positions are zero for the duration of its fall. Angle of attack and side slip are zero throughout, as there is only acceleration along the x-axis. At about 40 seconds after dropping the bowling ball, we predict it briefly breaks the sound barrier before slowing due to drag in a thickening atmosphere. So is this result physically accurate? We have not discussed the aerodynamics of a sphere, which is actually quite complex and variable. Effects like transition to turbulence and the buildup of shock waves in the transonic region can significantly change the drag coefficient. The transonic regime is a different aerodynamic regime than the subsonic. This brings into the question the validity of our aerodynamic model, which we've approximated with a constant drag coefficient of 0.5. As the ball falls, it's sure to heat up due to the friction with the atmosphere. And this heating can couple to the flow physics and therefore the aerodynamics of the sphere. This effect is obviously not included in this analysis. The drag coefficient of 0.5 is a reasonable approximation for small spheres, like a musket ball or a marble or a pea, even up to the point of supersonic flow. Staying away from this complex regime, let's consider dropping a blueberry from the top of the Eiffel Tower, where the highest observation deck is 906 meters. How fast will this berry go? And do you think it could pose a danger to someone below? With a simple release, it falls straight down, essentially at a constant rate, indicating it reaches its terminal velocity very quickly. And we can see this in the u-velocity plot, which predicts terminal velocity of approximately 16 meters per second or 36 miles per hour. Apart from ruining someone's clothes, this would clearly not pose a hazard. Now suppose the blueberry was thrown from the Eiffel Tower, not dropped, with 7 meters per second in both the y and z directions of the body axes. Pause for a moment and imagine the evolution of the blueberry velocity in the x direction, the y direction, and the z direction as it falls under gravity. The way to visualize this initial condition is first realize that VREL is in the body YZ plane. Then, angle of attack involves that left-hand rotation of the body y-axis through alpha so that VREL is in the XS-YS plane. Next, the angle of sideslip is the right-hand rotation of the stability axes about ZS through beta so that the x-axis aligns with VREL. The initial angle of attack is near 90 degrees because the throw creates an initial velocity vector perpendicular to the x body axis, and the initial angle of sideslip is 45 degrees. Both angle of attack and angle of sideslip subside to zero due to drag as the berry accelerates along the x-axis and decelerates along the body y and z axes. The Mach number dips briefly due to the deceleration of the berry in the horizontal plane before it accelerates to higher speed in the vertical direction to reach its terminal velocity. We observe the blueberry travels about 16 meters before drag fully dissipates its horizontal motion. We observe the same velocity profile in the u-velocity direction due to the interchange between drag and gravity. And in the body YZ plane, we observe velocity components v and w decay to zero due to drag arresting the horizontal motion. This is consistent with our expectations. The results of these simulations make sense, but there still could be errors in the code. In future lessons, we're going to be looking at other bodies like flying bricks to verify the angular dynamics. We'll compare these results to published NASA data intended to allow verification of flight simulations. To learn more, consult Stevens and Lewis, our primary reference. Access this lesson and more at learngnc.com. If you're a Patreon subscriber, thank you so much. You keep learngnc.com online and new content coming. If you're not a subscriber and you're interested in supporting the channel, or if you want access to all the codes used in this analysis, lesson previews, and other content, check out my Patreon page, Learn Guidance and Control. For less than the price of a 6-inch sandwich, you can gain access. So that's it. Thank you so much. Good luck. We'll see you next time.